I'm Ken Stanley, and I am a professor of computer science at the University of Central Florida. I'm also a senior research manager and staff scientist at Uber AI Labs. And I have been in AI for a long time. My particular area of interest and research has been in what's called neuroevolution, which is a combination of neural networks and evolutionary computation. I think this really hinges on ideas, and it's very hard to predict what good ideas there's going to be in the future. You can see certain trends, like you can see that there's promise in automation thanks in large part to reinforcement learning. You can imagine that gaining further steam and actually starting to impact how real-world processes work, like automating robots and autonomous vehicles and things like that. But I think those are kind of like, those kind of trends are less interesting because they're more obvious. I mean, we can all predict things like that. Like I think some more kind of subtle things that are interesting to think about are, will AI start to be really easy to optimize for people who don't know anything about AI? That would possibly really change the application and use of AI. And it's interesting how inaccessible AI is, like if you're not an expert. But it's also interesting how it's not clear why it should be inaccessible. Because at a low level, meaning like at the level of the code and the algorithms themselves, like at the level of like, what should the learning rates be? Like, should I be using SGD versus Atom or things like this? This is really technical minutia that like the average person like who hasn't been educated in this area would have no clue how to think about any of this. And all of that stuff seems to matter a lot. Like, it's like if to get the thing to really work, you really got to know this stuff. But like in some theoretical future, like you shouldn't have to really know about this stuff. It doesn't really have anything to do with what's interesting. Like the interesting things are actually at the high level, not the low level. Like what are the incentives that actually help something to like move in the direction of learning the thing I wanted to learn? And everybody has intuitions about incentives. I mean, like teachers have intuitions about incentives and like the reward systems and also just like what the curriculum should be. And if AI could shift towards where we can think about that at the level that we should be thinking about it, when we're thinking about what kind of things lead towards higher intelligence, then maybe it would become like a much, much more accessible kind of a thing and totally transform its application. Now, when the average person actually can like train an AI at home to do something that they want. So I think that's a kind of an interesting thing that maybe is on the horizon, but it doesn't get talked about that much. Yeah, so I've actually done some things to try to democratize AI, like in my own career. Like what I've done on sort of like as part of not my main research thrust, but kind of on the side for a number of years is like play with AI in video games, and that was one of the big motivations for me for doing that. Like different people have different reasons why they do AI in video games. I mean, one reason is just because it's kind of a risk-free platform, like no one's going to get killed or something like that. But for me, part of it is that like, if you get like some kind of sophisticated learning algorithm in a video game, where it's not just like the non-player character is smart, like that's just like a normal thing. Like here's a video game and wow, the enemies are really good. Like that's kind of just like the mundane thing you expect. But where it's actually not just that, but actually like learning, and actually learns in reaction to what you do as a player. So in some sense, what you do is actually affecting the trajectory of the learning and the training algorithm itself. Then it was just to me really interesting that in effect what you're doing is causing like just regular non-AI researchers to run real AI experiments. Like that's what they're effectively doing. And that just intrigues me that you can get this like kind of almost like crowdsourcing of effort into AI experiments if you could just create a platform, which is basically a game, which would incentivize people to do that because they just think they're having fun. And we created games like this. Like there was a game called Nero where you could train robots to go into a battle. And we saw, so the interface we gave them was different than like a program, of course, because we don't expect them to have to program. But like basically they had like some knobs they could turn and some levers and some dials where they could say like what gets rewarded and what gets penalized, and they could set up some scenarios just like with a graphical user interface. And they could like train using their robots to do different things. And what we saw that people would create scenarios, and they were quite complex, and they were often incremental, so they get harder and harder and harder, and then sometimes write them up like in a blog or something like that. And what was fascinating to me was these could have been research papers, but they just don't have all the research jargon. Like the people don't know anything under the hood, like what's all these technical things going on. But the high level of what's going on, like how did they set up the experiment? Like how did they get it to go from learning just to going to a flag to being able to dodge obstacles and dodge bullets and so forth, is like an actual complicated experiment with lots of steps. And like they would, enumerate these in a lot of detail because they're proud that they got their robots to do these things to share with the other players. And this is, I think, a really interesting and inspiring example of what could be possible in the future. Another example just worth mentioning is like the pick breeder experiment that we ran. And this was like a website where you can just breed pictures. But the kind of clever twist of that was that if you bred a picture, basically you would be evolving the pictures, like you choose a picture and it would have babies, and then you could choose the ones that you like and they would have children and so forth, and then you could like publish your picture on our website that you found by evolving it. But this clever twist is that you could then, someone else could come in, see your picture, and then branch and start evolving from there. So we had people evolving from where other people left off. And so it was kind of an experiment at some level. It is an experiment in evolutionary computation, but it's also an experiment in like mass level collaboration. Like huge, massive collaboration, but where there's no explicit collaboration. So nobody's talking to somebody else like, how am I going to work with you? Like, who should I work with? It's just, here's this artifact I discovered, hand it off to the world, and then someone else might take that baton and then move it forward again. And we got really, really large branching phylogenies is what you would call it, like trees of evolution, because people would branch off of people. And we could actually show it as a graph, like these huge phylogenies of pictures, basically, and just amazing pictures were discovered. Things that you wouldn't think that from just random blobs you could evolve things like cars and butterflies and skulls, and all kinds of very recognizable objects were evolved. And certainly it's some kind of a democratization, it's like humans in the loop. So it's kind of different from Nero in the sense it's like a many people experiment, but it has this extra element, which is that like there is a lot of potential for the combination of learning in humans, where we still are better at certain things than AI. But if we are put into the loop in certain very sensitive choice points, then we can add enormous value. The problem is that we're super expensive in the sense like we can't make millions of decisions like a computer can. Like we just can't afford that. We'd be exhausted. We're not fast enough. But the decisions we do make are really, really good. Often when intuition is involved, like, is this interesting or is that interesting? Like still humans are better than AI and that kind of thing. That's just exactly the kind of thing you want when you're evolving pictures. And so there is an opportunity there too in terms of democratization to find the right way to roll humans into the loop. So we're not exhausting them, we're not asking them to decide everything, but we just offer them a menu at just the right moment where like the AI is at a disadvantage and a human could possibly do better. Yeah, so I think we're seeing a phenomenon in evolutionary computation, which is a bit similar to what we saw in neural networks, which led to now what we call deep learning, but kind of just like offset a few years. In other words, evolution is happening a little bit later, maybe a decade later. And the phenomenon is just that computation unlocks a huge amount of potential, or computational power, that was latent and perhaps unrecognized before. And so like when you're doing things at a small scale, like a single CPU on a single computer, you don't see the full potential of certain kinds of very computationally hungry processes. And this is true of neural networks, and it's also true of evolution. And in neural networks, we've seen because of GPUs and also because of parallelization and just a general increase in processing power and lowering of expenses, so opening it up to more and more people to play with these kind of things, that it just completely transformed like what was possible. I mean, people were talking like 20 years ago about neural networks with backpropagation getting stuck on local optima and like really simple problems, and it was completely not exciting. And it wasn't even like the hot thing, even at the Neural Networks conference, to do neural networks, like a long time ago. But look at it now, and it's largely because there was an explosion in computation power, which happened to be aligned with what neural networks do and how they work, which showed that actually when you make the neural networks massive and you give them millions of examples, like the whole thing completely changes. And local optima are less of a problem, or maybe not even a problem at all in some cases, and so everything changes. And now that's why there's this revolution going on in machine learning. And now here's evolution, where it was similarly believed that it's sort of limited in scope and what it can actually do, and it's expensive in some ways. Perhaps like it doesn't have like the same principles as certain kinds of more formal kinds of processes that are based on sort of like analytic type of results. But there is this thing about evolution, which is very, very amenable to computation in the sense that it's just naturally parallel. So if you have a population of 1,000, in most kinds of situations, like you could just do 1,000 evaluations in parallel. So if you can give me 1,000 processors, then I basically can do an entire population in the time it takes to evaluate one individual. If you give me 10,000, then it's 10,000 to 1 and so forth. So it just scales linearly with number of processors, and sometimes even better if you have GPUs, where you can do like more than one at a time. And so it wasn't that, for whatever reason, that wasn't initially possible, or at least people didn't get the initiative to put together the resources to try this until just very recently. So it's kind of like 10 years after sort of the deep learning boom. But people started being like, well, look what happened in deep learning. Like maybe we can just like throw huge amounts of processing power at now an evolutionary population. And in some cases, this intersects with deep learning because they're evolving neural networks. So it's actually is both deep learning and evolution, or what I call neuroevolution. And maybe like with this, like, maybe 1,000-fold increases or even more in terms of power, like it'll change things. And that does seem to be the case, that now, we've seen, like in the last year or a couple of years, we've seen that like you actually can evolve networks with millions of connections inside of them. And that's like a huge jump from what we thought, which was like, oh, evolution kind of putters out at like a few thousand connections. Like it's just too high dimensional for what evolution does, which is basically like a sampling of the space, to possibly be able to make such a search tractable. But it turns out that if you have enough computational power in a large enough population, actually it can be tractable to optimize in these really high dimensional spaces. Of course, you can also combine evolution and gradient descent, which is what's used in deep learning too, which is also benefiting from the computational advances. So at the end of the day, what we have is just this whole new world that opened up like just in the last couple of years, where we did no longer understand the limitations. And so we don't actually know what it totally means, because we just recently have discovered that you can do these things. But it's certainly exciting because evolution is a different thing than gradient descent. And that means that like the kinds of cool stuff that can emerge from it are of a different qualitative type. It's true that they can also compete with each other directly, but it's probably not the best thinking to just think of them as a direct competition, but rather as probably complementary processes, like what goes on in conventional deep learning, what goes on in neuroevolution. And just they're qualitatively different things, but they're going to be good for different purposes. And this is really exciting that now we have this opportunity, like in industrial strength kind of problems, to apply this kind of technology, and it's a new thing. When it comes to evolutionary neural networks, something that has been really inspiring to me, and especially recently, is thinking about what's called open-endedness. And I think it's a very underappreciated challenge in the field of neuroevolution, evolutionary computation, and AI as a whole, and machine learning. And what it means is that there is a kind of an algorithm that isn't trying to solve a problem, but rather is trying to generate endless interesting things. So obviously this is some relation to novelty search and stuff like that. But like, it's not something that invents one thing, it's something that invents everything. And so you say, what kind of algorithm is that? Well, the kind of algorithm that is evolution on Earth, or natural evolution. It didn't solve a problem, it solved innumerable problems, and it continues to solve new problems. So what do I mean by problem? Like, I mean the problem of flight, the problem of photosynthesis, the problem of human level cognition. Like, all of these things were invented in the same run. That's what's amazing about it. This is one run of, if you think about the algorithm, just one run. This is completely different from like what we see in machine learning today, where it's like, here's a problem, let's solve it. And even in evolutionary computation, we tend to treat it that way. Let's see how powerful our algorithms are, we'll apply it to this benchmark problem, or let's get this robot to walk, or something like that. But it's just interesting that like in nature and in evolution in nature, what really defines evolution is its open-endedness. That's what's incredible about it. Not that it solves a particular problem you told it to solve. In fact, I think it wouldn't work if that was what you were trying to do, whatever that would mean. Like, for example, like if we started evolution on Earth with a single cell where presumably it started and we said, all right, let's get human level intelligence. Let's start working on this. So let's give them IQ tests. You know, like we're gonna just go let's go straight to the heart of the matter. Let's not go through all these silly things like flatworms and stuff like that. Well, I mean, that wouldn't work, obviously. The colony would die when you started throwing it at IQ tests. Just ridiculous. But it kind of illustrates that, like, you know, to get to these really, really far away branches of the tree of life, you cannot have an optimization process. You have to have an open-ended process. But those branches are worth getting to. And what's interesting is we don't have an algorithm like that, including in evolutionary computation. And for evolutionary computation, there's a particularly, I think, sensitive challenge because we're inspired by evolution in nature. So, like, if people say, like, oh, well, GAs aren't as good as X or Y or Z, it's like, well, maybe if we're talking about just like in terms of like beating this benchmark here, but GAs ultimately, or evolutionary algorithms in general, because GA is just one branch of that field, ultimately go back to something different, which is this open-endedness, which to me is profoundly more interesting than just solving a problem. Because what it is a never-ending algorithm. And that's like that's a term that Jean-Baptiste Murray coined in conversation with me that I like, sort of like illustrates what I'm talking about. Like that, you know, is there an algorithm that you would like to just press a button and say run, and where you would actually think it was worth like 1 billion years from now coming back and seeing what happened? And I would submit that there is no such algorithm. There's nothing where it's worth coming back 1 billion years from now. They would have all long converged or stagnated millions and millions of years before that. Wouldn't it be worth probably coming back 1 year from now, let alone 1 billion? Why can't we write an algorithm like that? I mean, Earth has been going for 1 billion years, at least the evolutionary part of it. And it's not done. It's still going. There has been no stagnation. There's been no stopping. There's been continual invention of absolutely amazing things, like things beyond the capabilities of human engineering, like intelligence, which is why we have the field of AI, or just all of the physical amazing things that animals can do, which robots cannot to this day. And so, can we actually trigger a process like that? It's probably the case. Not just that would be cool, because that's one reason to do it, because it is cool if we could just never-ending inventive processes, which is where evolution probably has a specific niche. I mean, in the whole world of machine learning. But also, this may be a key step on the path to artificial intelligence. You know, when you think about it, intelligence is one of those so far-off goals. You know, like the kind of like trying to make $1 billion kind of a thing. It's farther than that for sure, because people actually do that. That like it is one of those things where it's totally unclear what the path should be, and so you can't just say, well, this is an objective, we're just going to move towards it, and everybody be like, for all we know, like everything we've done in the field of machine learning is a completely deceptive path. Yeah, I mean, our Atari benchmarks have been going up, but that's like saying because you climb to the top of a tree, you're probably going to get to the moon, let alone the sun. So we may need something like open-endedness to create this proliferation of stepping stones that will give us like the seeds that we need to eventually grow into the AI. And so I think open-endedness stands as like a massive challenge for neuroevolution and evolutionary computation and the general field of AI, because it's not just evolution, but our brains are open-ended too, apparently. Like the history of human invention is a history of open-endedness as well. And so all of us in machine learning need to be thinking about open-endedness more, and I'm kind of hoping to raise the awareness of it because it's such a small community now that thinks about this, but it's such an exciting problem, and we have so many resources that we could use right now to try to pursue it. No one's kind of really looked at the question of, you know, it's sort of assumed like, well, look with the Atari, like Atari's been a big benchmark. In fact, that's sort of how DeepMind came on the scene with like these impressive Atari results with deep reinforcement learning. And so, but no one really looked at like, hey, well, maybe you can do that with evolution. Like, why do we assume that we can't do that? It's like, there's only one magic formula for doing that, or maybe there's more than one. So, but we know it's expensive though. I mean, you need big networks and so forth. But so let's just throw together, this is one of the thrusts behind our papers. Let's just throw together these like primitive algorithms, not fancy neuroevolution algorithms. We have fancy algorithms. But we said, let's just look at the primitive algorithms, like just a vanilla genetic algorithm or something, and just try to evolve really big neural networks. And just throw a lot of computation at it because we have access to a lot of computation now. And just see, maybe things will just work out okay. And lo and behold, like we got some really good results, competitive results in some cases, in some games. Of course, there's a whole suite of games, like in Atari, for example. In some of the games, we had state-of-the-art results from a GA, just a vanilla GA, on large neural networks that were way higher dimensional than what everybody, I think, almost anybody that I knew, assumed that an evolutionary algorithm could handle. And it just raised all kinds of questions, just by seeing that is actually possible. Like, what actually is the nature of these problems? I mean, it raises questions about the problems themselves. Like, what is DeepRL actually addressing, given that we now see that, like, a simple genetic algorithm can actually be competitive on some of these. And then again, when it's not competitive, like when the DeepRL or the deep learning conventional system does better, why is that? Like, what is the difference between the problems that evolution is better on and the problems that the DeepRL is better on? In terms of surprising results, probably the most shocking result that we found was that there were a few games where random search, so not a GA, just complete random search in this huge high-dimensional network space, was actually better than some very good, well-respected deep reinforcement learning algorithms. We looked at other things too, like in this 5 papers is a lot, so there's a whole bunch of stuff in there. Like, we did look at a little bit of, like, what if you take more sophisticated ideas from evolutionary and neuroevolutionary literature, like novelty search and novelty seeking, and kind of throw them into these, like, industrial scale systems and see if that can also give added benefit. And we saw that indeed that's true. And we also tried to propose some enhancements to like modern kinds of evolutionary algorithms that, like, sort of protect them from some of the criticisms about evolution. Like, for example, that, well, mutation's completely random, so it's unprincipled compared to SGD, which is actually looking at the gradient and following that in some kind of principled way. So we introduced, like, new kinds of mutation operators that actually are gradient-informed mutation operators. So it's kind of mixing paradigms in a way to make the point that, when we criticize evolutionary algorithms because, like, say, it's just random or something like that, it's kind of a myopic view. I mean, it's really short-sighted to think of it that way, when a lot of the overarching thinking about populations and mutation, not as just randomness, but as just a search operator, have all kinds of possibilities that are both motivated by nature and not motivated by nature, and can be informed by what we've learned in other areas like deep learning. And so there's just a huge amount of opportunity here for synergy between different ideas. The other thing I think we did was we tried to analyze some of the papers, a couple of the papers spent a lot of time analyzing what evolutionary algorithms actually are doing, particularly evolution strategies. A paper by OpenAI, which came before ours, really kind of brought to people's attention how powerful an evolution strategy can be. They were the first to show that these kinds of algorithms, evolution strategies in particular, could do well, not GAs, but evolution strategies like another variant, could do well in Atari and some other things. And so we wanted to understand, what is an evolution strategy really doing? So we did some kind of heavy analysis of it in comparison of it, like, for example, to gradient descent, to understand. And so if you're interested in that, if you look at the suite of papers, you can find like really, really careful head-to-head kinds of comparisons, like what does ES, or evolution strategy, do on a single step versus like SGD, and how do they differ? How much does this approximate what this does, and how much does it actually matter that they don't do exactly the same thing? And so a lot of kind of analysis is also in that suite of papers. Yeah, so novelty search is an algorithm that I worked on with Joel Lehman when he was my PhD student. And it is really, I think, a kind of a deep suggestion about the nature of search and what kinds of searches actually succeed in doing really, really interesting or amazing things. And the problem that it kind of addresses is the problem that if I set an objective, like I say, this is what I'm trying to accomplish, and then I have some gradient that I follow to try to get to the objective, which is to a large extent, what almost the entire field of machine learning was doing, say almost, because there's some exceptions, but was doing up until a couple of years ago, is just, obviously it makes sense. Let's set an objective and then follow some kind of path to the objective. And that's just like, well, that's what we're trying to achieve, so that's what we should do. But actually it turns out that there's a lot of problems with doing things like that. In fact, the problems can be so serious that it's really a bad idea. In other words, and this is where it gets kind of deep, is like, sometimes the best way to actually solve your problems is to not try to solve your problems. And it sounds almost like something out of a fortune cookie or something. But the reason is because the world is deceptive. And deception is a concept in search, but it's also just a general concept in life, but it's maybe not recognized how serious the problem is, at least in general. In machine learning it wasn't, which is just that it can appear that you are doing better. In other words, you're following a path where some performance metric is going up, but you're actually going in the wrong direction. This happens all the time. It's called deception. It happens in machine learning too. And so it leads to what's called like local optima. I mean, people know about this, but what people didn't really recognize and appreciate is just how profound deception is. That it's just absolutely everywhere. And it's not just in machine learning, it's in your whole life. I mean, like, and you avoid it to some extent by not trying to do things that are too ambitious. But if you start trying to do things that are really ambitious, you'll run into it. You know, like you might say, well, okay, my goal is to be a billionaire or something. Okay, well, now let's measure every decision you make against whether it actually increases your salary. And then think about whether that's going to lead you to becoming a billionaire. I mean, almost certainly not, because the gradient you should be following to get to be a billionaire is probably orthogonal to your salary. It has nothing to do with that. Like, even if you double your salary, it has nothing to do with whether you're going to be a billionaire. And we get caught in these paradoxes all the time, including objective functions in machine learning. And so why did we think about this? Like, this was something that I hadn't been thinking about at all. But the pig breeder experiment that I alluded to earlier when we were talking a little bit about democratization is actually what revealed this to us in like kind of a stark way. And it was really an epiphany for me when I saw this phenomenon. I didn't know about it before, but what we discovered when we were looking at the pig breeder, the database of images that people had evolved, is we discovered that in every case where something really cool was discovered, like say a car or a butterfly or something like that, there is some predecessor image, in other words, an ancestor, where the person who discovered that ancestor was not trying to get the thing that was ultimately discovered. And this is like 99.99% of cases. And like we could tell this because we could look at the images and see. So we could see that, for example, and this is actually one that I evolved, so I knew this one. This is actually the one that triggered the realization to me, is I evolved something that looked like an alien. I evolved something that looked like a car, but I had started from an alien face. And I never would have thought this alien face could turn into a car. But what's kind of paradoxical here is if I had wanted a car, I would not have started at an alien face. Because the alien face doesn't look like a car. So if I was like, oh, I need to get a car, like there's no way I'm going to start with the alien face. So it was because I was not trying to evolve the car that I got the car. And we can see that this is the case because we can see all the images of everything that's ever been evolved. That this is like the consistent story. Now, when this happened to me and I saw this, I couldn't stop thinking about it. You know, I was like, it's just like went against everything I've ever been taught. You know, I was like, well, this is so crazy that like the only way I could get this if I was not trying to get it. But like all the algorithms that I set up this fitness function or this objective function where it's like, it just rewards you for getting closer to what it's trying to do. And so something is seriously wrong if there's this whole world of things that you can't actually discover if you're trying to do what you actually want to do. And so I was like, well, what actually did happen in this case? Or what is actually going on in Pick Breeder? And this is what led to the novelty search algorithm, which is this recognition that there are other gradients in the world, and that sometimes you have to be following the other. By other, I mean not the objective gradient, not the thing that leads to where you're hoping to go, but something that leads somewhere along a different line, but which has value anyway. And these are gradients that we just don't think a lot about, or at least we didn't up until a couple of years ago. And this is true both in deep learning and in neuroevolution. In deep learning, the people have started to recognize the importance of curiosity and so forth, like in deep RL and stuff like that. But just a few years ago, this wasn't a widely recognized thing, you know, with some exceptions, like Schmidhuber going back to the 90s with his curiosity research. But generally, people just set objective functions, not really worrying about this issue. But now I was like, there's got to be a whole world of things you can't get to that way. And so what are these other gradients, you know? Because like, it's not the case that like you're just doing things that are random. Like people in PicBreed are not doing things that are random. It's not like just clicking randomly on images, just hoping something good happens. They're obviously doing things for some reason. Why are they doing them? Because they're interesting. It's like if I click on this and then it leads to like some pattern like that's symmetric or something, and I like it, it's not because I'm like, oh, well, now I'm going to get a butterfly. It's because the pattern in its own right is just interesting to me. And this is not like a random fact. This is based on like the full force of all of my intelligence is still being put on to making this decision that I like this pattern. So it's hardly a trivial gradient that I'm following. But that leads to stepping stones, things that can lead to other things. And the more stepping stones you have access to, the more places you can get. And so it is by following these gradients of interestingness that leads to this branching process of more and more stepping stones proliferating, that we get to more and more stepping stones, that suddenly it becomes possible to find something like a car in PicBreeder. And so what I was thinking was, what is there like interestingness, like a gradient like that would work this way? And novelty is kind of a proxy for it. Novelty is not equivalent to interestingness. Interestingness is richer and also harder to formalize, but novelty is kind of close to what interestingness is. And so the idea is, what if you only followed gradients of novelty? And novelty is just really fascinating as a gradient, you know, because it's actually very well informed, because it's basically a comparison of where you are to where you were in the past. And so it's actually just really the opposite of an objective, because an objective is comparing where you are to where you want to be in the future. But neither has more information. Like people have this intuition when they hear about this that novelty search is kind of random, but objective search is like not random because you're comparing to the objective. But that couldn't be further from the case. I mean, there's actually more information about the past than the future because it actually was there. So I know what I actually had. And so I can compute novelty with respect to some record of where I've been in the past and have a very defined gradient. And then the question we asked was, what if you only did that? You know, not just we'll use it as kind of a helper, which is something people have done also recently in a number of fields, but forget about being a helper. Let's be really radical about this and like only search for a novelty and just forget objectives entirely. And you know, you might think, well, that's just crazy. Like, what could you possibly find? But we found that in some problems, you actually get better solutions than if you were trying to solve the problem with an objective. And this is in machine learning, which I think is a really profound result. I mean, it's just like just mind-boggling and paradoxical and makes you think. And so, you know, we started to think like these fortune cookie types of statements, like to achieve your highest goals, you have to be willing to abandon them. And it's obviously not going to always be true, but it is true in some cases, and it helps to illustrate for us. I think it's not, the point isn't novelty is better than an objective. That would be a naive thing, because obviously the combination of them is probably where the real pay is at in the long run. But what it illustrates when you sometimes win with novelty is just how profoundly weak objectives are in terms of like really being a good guiding light. You know, they're just so much less than you think they are. Like it's an absolute embarrassment for objectives that something that doesn't even know what problem it's trying to solve is doing better at solving the problem than the objectively driven version of the same exact algorithm. That is just an absolute embarrassment. And the reason is because, like if you think about it, the stepping stones that lead to where you may want to go are only accessible to you if you open your mind and are willing to actually accept things that don't look better objectively. So I like to give the example of walking. Like on the road to learning to walk, you have to learn about oscillation. But if you just start oscillating your legs while you're standing or something like that, you'll just fall on your face. And so if objectively I was saying, well, how good are you at moving as far as you can from A to B? You get a 0. But if I look at it from like, is that interesting? It's very interesting. That's a completely new idea. I've never seen that before. So in the novelty version of the world, I would be like, okay, let's go down that path. I don't know where this leads, but it's something I haven't seen before. But in the objective version of the world, I'm like, nope, try something else. So what will I try? Like, I'll try like lunging as far as I can, or something that's in the short term, like looks like I'm actually making progress, but in the long run, it's going nowhere because you're not going to be able to walk based on just like throwing your body forward as fast as you can. So it turns out that in some domains that actually does work. But the larger lesson is just like, let's take seriously other gradients like the gradient of novelty. And it's true that this has led to people combining them. Like now we call it QD in evolutionary computations, or quality diversity. Like a notion of quality, which is like an objective notion, a notion of diversity, like novelty. And we try to put them together in a smart way, which is in its own right a tricky thing, because the objectives tend to overwhelm the diversity components if you're not careful. But now at least we can understand that this is something we can aspire to and be more sophisticated in our search. and also think about what it means just in general about how we go about our life. Like, that's why we actually wrote a whole book about this called Why Greatness Cannot Be Planned. It's not even about just computer science. It's just the recognition that, like, if you think about it, our whole society runs this way. Like, granting agencies are based on objective criteria. They say the first thing they want to know is define your objectives. Tell us how you're going to get there. We'll evaluate your grant and whether we're going to give you money based on, like, the likelihood that this is going to work. Like, how terrible is that when we now understand that sometimes the best way to actually get innovation is to not follow the objective gradient. So this is just totally ridiculous, the way we're running things in our society. And there's so many things in your life that are objectively driven. It's like anytime you do anything, someone says, well, what are you trying to accomplish? What will you accomplish? What is the payoff going to be? Why are you doing this? Like, from the moment you choose your major, or even where you're going to go to school and so on throughout your entire life, and even grades that you get from the time you enter kindergarten. So this is a really, I think, deep and all-encompassing principle that novelty search touches on, that's worth a lot of thought, and still worth a lot of thought today, that it's just, I don't even think we fully absorbed all the implications of it.